Hello everyone, we are back. Let's go to our last talk today. I would like to invite Professor Sandro Ferreira from Unicinos to present the speaker, please.
Thanks, Alexandra. Thanks for the invitation. It's very nice to be here. I'm Professor Sandro from Unicinos University, and to me, this is really a pleasure to introduce Professor Arjuna. I myself work a little bit with analog signal processing, and he's bringing to us this very interesting topic, like the rebirth of analog signal processing in these times of accelerated computer aging. Professor Arjuna is an associate professor of electrical engineer from the Florida International University. He got his Ph.D. at University of Calgary, Canada, and B.Sc with highest honors in Moratuwa, Sri Lanka. His research interests are in wireless communication, signal processing, RF signal processing, 5G and 6G topics, and digital VLSI signal computing. And so continue just to finish that. This program he's working currently is supported by DARPA, official of Naval Research, NSA, NASA, and NSF. So, well, thanks for coming, Professor. The floor is yours.
Thank you so much for the introduction. So, all right, so let me slowly get fired up. Can you guys all see my screen fully? I guess that's visible. Okay, that's fine. All right, so let me open it. Okay. So good afternoon, everyone. Great pleasure being here. And first of all, let me thank everyone, the organization, IEEE, Trio, and the Young Professionals Workshop for inviting me. So my name is Arjuna Madayake. I am an associate professor at Florida International, and I will be trying to tell you a little bit about some of the things that we have been trying in the realm of analog computing in our research group in the last couple of years. Okay. So first of all, this is a massive effort among many people. I am by no means the only one working on it. So just a quick thank you to all my collaborators and students. I won't go through the whole list, but as you can see, so many people have contributed over the years to make this work possible. So thank you so much to everyone. To begin a brief outline of the talk, so I will dedicate a slide just to talk about the background of analog computing and what some of the exciting things that are happening in modern analog computing. Before getting into the specifics of this work. Then we will give a brief introduction of two methods that we've developed as part of our DARPA project, which we call continuous time algorithms in Laplace domain and all-pass delay approximation method. So we'll get into the details of that, and I'll explain in full glory what we are trying to do for both these methods. So that will be a little bit of math. So I think that's a good thing. I want to include quite a bit of math so that we firmly ground what we are doing in some theoretical framework. Then we'll move on to circuits and systems topics. We'll look at some basic circuits that we've designed and fabricated and how we've tested them, what are the challenges in measurement, calibration, noise, distortion. And another big challenge in computing is how do you compare a particular computing system that you dreamed up with the state of the art. It's not so easy as it might sound. Then we'll look at some new work that we are currently doing as the final part of our DARPA project. where we move from linear systems into nonlinear systems, especially nonlinear partial differential equations, and some ongoing work on that topic, and finally conclusions. All right, so analog computing, it turns out, predates digital computing, right? So there are many instances where a lot of numerical calculations have been done very reliably, actually, using analog computing, especially during World War II. So we know that the digital computer, like ENIAC, was developed in the 1940s, but World War II happened, 5-6 years before that. And especially in naval warfare, when they wanted to target long-range projectiles and things like that, analog computers, and especially mechanical analog computers, as well as electrical vacuum tube-based analog computers, were used for this kind of thing. Of course, after the digital computer was born, we saw Moore's law take off with integrated circuits and transistors and all that stuff. And there was massive growth in the digital computing realm, and analog computing was forgotten. Forgotten, but not by all, okay? So the interesting thing is that even though digital computers took off exponentially, it turns out that analog technologies also took off exponentially, pretty much, even though we haven't really used that for computing. I mean, for example, in the 1930s or 1940s, you might think a megahertz would be a very high frequency, but these days people are talking about terahertz, right, and hundreds of gigahertz. So the technologies have really moved forward. So we are asking the question, now that the Moore's law is slowing down a little bit and going from exponential to something more like linear, can we go back and see, did we miss something? Could we perhaps exploit some of the rapidly growing analog techniques to supplement the digital computing parts so that we can get better throughput overall? So this is the bigger question that we are trying to answer in terms of solving computational problems, especially partial differential equations in this project. So we'll talk about partial differential equations in depth. But before we do, I just want to mention that analog computing has made a big comeback in machine learning and artificial intelligence, especially the approach called in-memory computing, right? IMC is really taking off, and people are finding that, especially for low precision inference, in-memory computing might be a very good idea. So I just wanted to mention that, because the analog computing that we are going to talk about today is not for AI or machine learning, it is for scientific computing. But we have to be cognizant that analog computing is also making a massive comeback for machine learning. So I'll leave it at that for now. We do work on this area also, but that's for another day. Okay, so the main topic of today's talk is the use of integrated circuits, custom integrated circuits in analog computing for solving various types of partial differential equations. So what is the motivation for this? So we know that physics models, especially classical physics models, for various complicated systems like future realizations of nuclear fusion for clean energy, requires very complicated classical physics models to be computed. For example, if you want to do a full simulation of a nuclear fusion reaction for clean energy, that computation might take several weeks or months in a state-of-the-art computer. So the question is, can we use analog computing or some deviant or version of analog computing to make an accelerator that will work together with the digital computing, supercomputing solution to get a little bit more throughput and perhaps get a result 10 times faster, but with some compromise in accuracy, right? We know that analog computing is not great for accuracy, but it's good for speed and power. So this is the motivation of the talk. So of course, nuclear fusion equations are extremely complicated. So we have started out with something simpler, basically linear Maxwell's equations. So we know that Maxwell's equations are first order equations that model all of electromagnetic behavior in the linear applications. So the focus of our work is to explore how analog computers can be potentially used to accelerate some of the computational electromagnetic simulations for linear applications, right? Like antennas and wireless communications, radar, all these things are linear applications. So we have a vision. So the analog computer that we design is very, very efficient at doing a particular task. But it is by no means a general replacement for analog, for all computing, right? No one is trying to say that we can replace digital computers with analog ones. That's not the idea. So if you take a scientific computing problem or a physics problem, you might be able to identify some physics models, like based on partial differential equation systems, which are well suited for mapping into various types of circuits and systems technologies. So this makes a distinction from GPUs, for example, right? Because GPUs are excellent for matrix vector computations, but not so good for recursive computations, for example. So we might be able to find physics models which are natively supported, natively explained in terms of PDEs, and we want to map those PDEs into continuous time analog circuits so that we have a natural fit that can lead to better efficiency and speed in terms of computing the partial differential equation system. So of course, this is a mixed domain realization. We have analog parts and digital parts, and we want to be able to program everything with certain amount of flexibility. We want to be able to get data in, get data out. So it's an analog digital hybrid computing platform where parts of the computation and data management, programming and calibration occurs in digital, and the brute force numerical computation happens in an analog system. So in our Envision system, we have a multi-chip analog computing board shown in the middle. So it forms a systolic array. That means it's analog, but it contains multiple parallel identical chips which are interconnected in a particular way. And the computation happens in the analog part, but you have a whole lot of high-speed radio frequency or RF digital I/O analog. I'm sorry, not digital. Analog input and output ports that are fed into FPGAs. So we use technologies like the radio frequency system on chip, RF SoCs, which has inbuilt high-speed ADCs and DACs on board to do that kind of high-speed communication with the analog processor. So we'll show you the details. But first, some math. So, okay. So we are going to look at a simplified version of analog computing for scientific purposes, and that simplified version deals with linear Maxwell's equations. Okay, so I'll show you the Maxwell's equations just for you to recall what it looks like in a second. But for now, we are going to talk about two approaches. The first approach is an analog computing approach which we derive using Laplace transform techniques. The second approach is an extension of a very well-known discrete time computation scheme used in computational electromagnetics known as finite difference time domain, or FDTD. So finite difference time domain has the advantage that it can be extended to nonlinear systems, whereas the first method based on Laplace domain is limited to linear systems. So we talk about both, but we will concentrate more on the finite difference time domain algorithm mapped to analog circuits because it has a future for the nonlinear systems that we want to do in the future. So very briefly, Maxwell's equations model the electric and magnetic fields in space and time. It provides 4 coupled first-order equations. And we know that from the antennas and electromagnetics community that the wave equation is a very simple version of the solution of a general finite difference time domain system. So in our work, we simplified the problem, and we are using the wave equation number 3 as a model to show what analog computing can potentially achieve as a technology. Right? Okay, so the wave equation is a two variable equation. For example, in this case, the 1D wave equation has a spatial variable x and a time t, and we have mu and epsilon that are the dielectric and permittivity and the permeability of the material, and it's related to the speed of light c using well-known 1 over mu epsilon equals c squared equation. So equation 4 is representative of a wide range of finite difference time domain problems. It's simplified, but it makes the point. So in the first technique, where we are going to use the Laplace domain, what we do is we take the wave equation and we discretize the spatial dimension. So x is discretized using a finite difference operator shown in equation 5, but we leave the time domain alone. It's still in continuous time. So unlike finite difference time domain, where we discretize time and space both, in our circuit, we only discretize space, we leave time continuous. So when you do that, we get something very interesting. We can apply the Laplace transform along the time dimension and do some basic rearranging, algebraic manipulation of the wave equation. And to cut a long story short, we can get into equation 8. So equation 8 is a Laplace function because it has the S term, but also it's a multi-input, multi-output linear combination. So what that means is you can now synthesize using simple circuit synthesis techniques a multi-input, multi-output analog circuit which has some LRC behavior, some second-order resonance behavior. But the multi-input, multi-output nature of this system allows parallel processing because you can connect computational nodes between neighbors. So equation 8 is the governing equation, and you can think of it as a repeating tile that you can create on chip, and the tiles are interconnected only across nearest neighbors, which makes it locally interconnected and highly parallel. So our building block in the Laplace domain looks like a simple circuit, and you can use an op-amp to represent the behavior. But in practice, it does not have to be an op-amp. It can be any high-gain circuit element. Okay, so you have a bunch of inputs shown on the left, Vi plus 1 and Vi minus 1 of t, and we have an output Vi of t. Okay, so I minus 1 and I plus 1 refer to spatial neighboring computational nodes, and Vi of t represents the output at the present spatial location given by index I. So you can see that it's a linear continuous time circuit. It's got an inductor L and a capacitor C, so which makes it a resonance circuit. So you can create a circuit. You don't need actual inductors. You can use the inductance replacement techniques using RC active filter methods. And you can create a transistor-only RC circuit, RC active circuit on chip to mimic this behavior. And we call it the internal module, or IM, and it's got a Laplace function. So every intermediate or internal module represents a particular location in your electromagnetic computational grid. Now, along the spatial dimension, we haven't discretized, which makes everything continuous in time. That means fully analog. There's no quantization and there's no sampling along time dimension. But the whole problem is sampled along the spatial dimension because the spatial dimension has been discretized using a suitable discretization operator. So what you get is a systolic array of analog parallel processing modules which are interconnected in a particular way so that the coupling that's needed for Maxwell's equations is realized in parallel. But when you provide inputs in real time, the circuit provides the computation in real time at the output. Of course, you have to deal with various complexities like boundary conditions. So boundary conditions need a separate circuit. We won't go into the details of that, but that's available in all the papers that we have published. So suffice it to say that you can map your finite difference time domain algorithm, but now the time domain is not finite difference, it is continuous in Laplace, and that into a fully parallel, massively parallel analog circuit that computes in real time. Okay, so that's for the Laplace technique. Now I'm going to take a step back and say, okay, I'm not going to do the Laplace technique anymore because that limits us in the future to linear systems. I want to be more ambitious and say I want to extend my model, my technique into things like magnetohydrodynamics, which is a nonlinear system. So in which case we have to start with the technology that supports nonlinearities. Okay. So the way to do that is to go to the original finite difference time domain technique where both space and time is discrete. But now, without realizing the discrete time in a digital computer, what we do is we replace the discrete time with a continuous time delay or wideband delay. And it turns out that using analog RC active circuits, you can make continuous time delays using all-pass filters. So I won't go through all the math here, but you can look at the slides slowly. To cut a long story short, what we do is we replace the time delay in the finite difference time domain operator with a continuous time version that is analog. Okay, so it's a repeating function. So your frequency response wraps because it's sampled in time in a sense, but it's realized in a continuous time delay. But the delays can be realized using wideband delay circuits using all-pass filters. So that looks similar to what I said earlier, but notice there are no more LC circuits. This is not a resonance circuit as such, but we have the phi of S, which we call our all-pass filter function. So what we do is, ideally, if we have a delay tau, we know that the Laplace transform of a delay tau is e to the power minus s tau, where e is the exponential function, right? So you can use the Taylor series approximation and find various approximations of the ideal delay using a finite order analog filter. So we've done some work on that, and we know that we can in fact very, very nicely approximate wideband delays using only third order all-pass filters. So we won't go into the details of that. That's available in the literature, but these functions that show as e to the minus s tau is actually just 3 first order all-pass filters in cascade. And you can make these first order all-pass filters to have very high bandwidth in analog CMOS circuits. All right, so we talked about the 2 different approaches. Now the question is, once you make your analog circuit, how do you know whether it's working properly? Because our computational technique is new, there is no standard method. So we went out and we looked in the literature, we couldn't find anything standard. So we tried to adapt a couple of metrics just for us to understand how well it's working. So we looked at 2 metrics. The first metric is a mean square difference. So we look at the ideal output from, let's say, MATLAB using finite difference time domain algorithms. And then we get the output from, let's say, our cadence simulation or something like that of the analog circuit, and we find out what the difference is, and we square and sum that difference to get a error metric. Also, we looked at it in terms of a signal to noise ratio degradation. So you can think of an ideal computation having some input signal to noise ratio coming from our inputs, which has their own SNR at the input lines, right? And when you do your computation, the computation is not ideal, so it adds noise and distortion. So it kinds of worsens the output signal to noise ratio by some amount of dB. So can we think of it as something like a noise figure of your computing platform, a metric that will give you a handle on how bad it is, right? Ideally, it should be completely noise-free, but we know that analog circuits are never completely noise-free. So we expressed this gamma metric to be able to find some measurement of how bad your signal-to-noise energies are going to be at the input and output. So we'll talk about that. So here are some simulations. So we are modeling the propagation of an electromagnetic wave along x direction using Maxwell's equations, but it's in the form of the wave equation. So we have a propagation scenario in the middle of the computation, but boundary conditions at the ends of the computation. So both the propagation part and the boundary conditions are realized using special analog RC active circuits, which we can design. And we expressed 3 types of boundary conditions in our experiment. So there are many different boundary conditions, but in electromagnetics, there are some well-known basic ones: the radiation boundary condition, the Neumann boundary condition, and the Dirichlet boundary condition. So our circuits can be reconfigured to mimic all 3 types. So we can show the plan view and the top view or 3D view on the left. And on the right, we computed the accuracy, how good the analog computer is compared to a MATLAB version, both as a mean squared error and as a decibel value shown on the left. So the red curve is the decibel value. The blue curves are the mean squared error. So you can see a little bit weird realization. So depending on which spatial location you are at, the performance seems to be different. And in general, the more you compute, the bigger your computational grid, errors tend to accumulate and the performance seems to get worse and worse. So that seems to be a problem in this type of analog computer, because if your computational grids are really big, then errors tend to accumulate, and that can lead to a total aggregate error that might be too big for the particular application. So that's a problem. But anyway, so this is what we did. And now I'll tell you a little bit about the circuits, right? So we are talking about computing the finite difference time domain algorithm, but it's finite difference in space, but along time it's continuous, right? And we are using first order all pass filters, a cascade of first order all pass filters, to mimic an ideal infinite order wideband delay. So by doing that, we have this fully parallel multi-input, multi-output analog circuit that can be replicated very tightly on a CMOS platform and coupled using on-chip connections. And that coupling tells the circuit what the overall algorithm is. But each circuit itself describes in circuits and systems form the behavior of the electric and magnetic fields and how they are interrelated at that particular location. So it's basically a linear circuit per module, but in general, you can do nonlinear circuits too. We'll come to that later, right? So we have this parallel circuit. So we can see that these IM are the internal modules, or these are analog. And the IMs are interconnected between their nearest neighbors using a crisscross connection. So the crisscross connection shows connections both to and from all the neighbors. And that's what allows things like reflections. For example, if your computation proceeds from the left-hand side and hits the boundary value problem at the right-hand side of the computation, there could be part of the energy is transmitted and part of the energy is reflected, right? And that reflected part comes back as a reflected wave back into the computation. And what you observe as a voltage is the interference of all the reflections that occur at that point. So that has to be taken into account. So that's why we have this crisscross connection between analog modules in both directions, and it works pretty well. So some details of the solver. So in our first experiment, we used a cheap process, a 22-year-old process, 180 nanometer CMOS from TSMC. And the only reason why we used it, because it's very cheap, it's affordable, right? And the results that we show are for this 180 nanometer process. But of course, we expect that better performance can be achieved using 90 nanometer or 65, something like that. So we designed the system to have a real-time bandwidth of 50 megahertz. So that means 50 million inputs per second. And we chose a particular computational grid. We used finite difference time domain techniques to find what the time step should be. So it turns out that for this particular simulation, the time step has to be 1.6 nanoseconds. So in order for all the conditions of finite difference time domain stability to be satisfied and to sustain a 50 megahertz input, our analog computing op-amp circuit has to have a bandwidth of at least 625 megahertz, a fairly high wideband circuit. So it turns out that it is possible to create this complicated circuit with that bandwidth, but it took quite a bit of effort. So we won't go through the details of designing the op-amp and things like that, but I think the op-amp had more than 700 megahertz of gain bandwidth product. So anyway, so we have this analog circuit done in 180 nanometer CMOS. And I said that the time domain is realized using wideband delays. And the wideband delays are approximated using a Taylor series approach, right? So if you look at the first line, the Laplace domain representation of e to the minus s tau in the update equations can be approximated in the form using m identical first order all pass sections. So m is an integer, and each of these components has a 1 minus s over 1 plus s form. It's a first order all pass filter. And in previous work, we know that even though mathematically m has to be infinite in order for this to be exactly equal, in practice, 3 sections are more than enough to get it to work properly. So for all practical purposes, m is 3, and 3 is more than fine. So ultimately what we do is everywhere we have an extremely wideband delay circuit in analog, which is unrealizable circuit theoretically speaking, we can approximate that using a third order all pass filter. And that third order all pass filter also is a cascade of 3 first order all pass filters, which makes it extremely easy to design in CMOS. So we've done that. So on the top, we show the general approach of doing that. It's a differential mode circuit, so that's why you need the subtractor at the output. So we've designed it so that we can actually tune the delay and the gain of the all-pass filter. So I've shown some results of a 50 megahertz bandwidth all-pass filter, how that can be tuned from gains of plus 2 dB to minus 4 dB. And the delay also can be tuned across a range. And that's important because you'll find that when you're trying to build these analog computers, the process variations and everything else makes none of these circuits are identical to each other, right? So in order for everything to work properly, there's a fairly complicated, very tedious calibration algorithm, and every single variable in that circuit has to be properly calibrated. And for that to happen, we need to make everything tunable, which can be a bit of a pain to design and to do. But nevertheless, we've done it. And we can control the gain and the delay of every analog all-pass filter individually. And that allows us to calibrate things very, very carefully. Okay, so we've shown tunability. So this is the basic building block in a particular module. So if you take one internal module, there are multiple delay stages consisting of all-pass filters, and the interconnection is what describes the finite difference time domain algorithm. And all the gains are programmable using capacitive DAC techniques. So I won't get into the details. The details are available in our JCC paper. So to move along, this is the full circuit diagram without, of course, the bias details of one internal module. And every internal module consists of a large number of op-amps in order for everything to work properly. Everything is programmable using capacitive DACs, and all the gains and phases and delays can be individually tweaked actually under software control, because all the controllable values are fed by capacitive DACs, and they have register bits that can be controlled. So it has a lot of programmability in order for calibration to be possible. So this is the chip that actually worked. It's our second chip. The first chip didn't work properly, but second one did. So this is it has a test bandwidth of 30 megahertz. It consumes 200 milliwatts of power, and it supports 16 spatial locations in parallel. So we could have done more spatial locations, but just to keep costs down and to prove the concept, we went with 16. Everything is digitally programmable, and digitally calibration can be done. And we can cascade multiple chips to get a larger computational grid if we so want. Okay. So this is the layout, fabricated chip. This is the full system. So on the left-hand side, you can see the analog chip that we fabricated in the middle, sitting in the middle. And there are phase coherent RF lines going out in a circle. So we had to keep all the lines equal length because it's operating at high frequencies, radio frequencies. So you want to maintain phase coherence very accurately. And that whole thing is fed by some mini circuits blocks that just to get the voltage levels right, that can be processed by our FPGA platforms. So these are Vertex 6, I think, quite old. These particular ones are from the radio astronomy community called Roach boards, very powerful systems. And we use 2 of them with multiple high-speed DACs and ADCs to do calibration and data processing. So the whole system has lots of FPGAs for support work, but the actual computation happens in that analog chip. So these are the measurements. These are from the actual chip done in real time. So I think the long story short is that it works. It proves the concept. It's not perfect, but it works. So we observed various ranges of error. Some spatial locations are within 1% of the MATLAB, whereas some other locations are about 10%. So on average, it's about 5-6% accurate. So it's not super accurate. So if you want something that's extremely precise, then this is not a good idea. But if you want to do something very fast at very low power and are okay with some amount of compromise in terms of the accuracy, for example, in fast edge computing, this seems to work. So all the details are fully explained in the journal paper. I don't have the time to go through all the details, but suffice it to say that it's working in real time. Some comparisons. So it turns out that analog computing has been very well investigated by other people, and there are various results available in the literature. So we tried to compare what we did with some of the literature as fairly as possible. So our chip supports 30 megahertz of bandwidth with the computational bandwidth of more than 600 megahertz, whereas the other chips are actually quite slow. And the reason is we wanted to do, our chip was designed to do radio frequency computation at the cost of programmability. So if you want to make things more and more flexible and more programmable, then you are going to get a hit in the speed that you can achieve. So it's a compromise. But it's very low power. So I will show you the comparison with GPUs in the next slide. So these are some other results from another set of results from the literature. So we can get 333 megahertz per square millimeter at 10 watts, whereas some of the other chips are having different values. So the comparison is a little complicated, but in general, we can outperform most of the literature out there. So what's interesting is, in the earlier graphs, we showed how the new chip compared with other analog computing platforms. But it's also important to see how our chips will compare with existing digital technologies. For example, high-performance GPUs, high-performance Linux CPUs running Red Hat 64, things like that. So we did the performance, and we found that for the same algorithm, finite difference time domain, for the same time step, running on an NVIDIA GeForce GPU, the analog computing chip is 420 times faster in terms of pure raw speed, and 1,000th the power consumption. Now that may sound fantastic, but we have to remember that GPUs are good at matrix vector computations. They are not very good at recursive partial differential equations. Also, GPUs are extremely programmable and user-friendly, whereas our chip is not that programmable, and it is certainly not user-friendly. So there's a compromise, but the take-home message is that if you really want something that has extreme efficiency, extremely low power, very high throughput, and you can take a hit in accuracy, then this type of specialized analog computer chip might be suitable. But it's not suitable for every computation and every application. Okay, so it's a trade-off. So we also wanted to compare with FPGAs. So we wanted to see, is this really that fast, or can FPGAs do better, or are they comparable? So in order to solve that question, we went and bought the best available FPGA that was in the market at the time, and that is the Xilinx radio frequency system on chip RF-SoC platform. In this case, this is a GCU 1275. It's a $25,000 board. So that's the best that money can buy. So we did that comparison because we wanted to really pitch the chip against the best available FPGA technology out there. And the Xilinx RF-SoC was the best at the time. So it turns out that the speed improvements is about 3 times, 2.8. So not as good as against GPUs, but still about 3 times faster. But when you normalize to power consumption, it's about 28 times better. So still, the analog computer can beat state-of-the-art FPGAs. Now remember, our chip is 180 nanometer, and these Xilinx chips are like, I think, 22 or something. So it's really not a fair comparison, but we did the best we could. And we find that for edge computing, again, it may meet or exceed state-of-the-art digital under some conditions. So finally, very briefly, so that's it for linear Maxwell's equations. So I want to tell you a little bit about what we are doing now in terms of nonlinear partial differential equation systems. So the partial differential equation systems which are nonlinear are we have this technique where, there's a particular class of nonlinear partial differential equation system called conservative systems, conservative form. And there are standard techniques in the differential, using differential operators, McCormick operators, things like that, that can be used for solving them. So we use the standard two-step continuous time technique, two-step McCormack's technique implemented in continuous time. So again, the trick is to replace the delays with continuous time delays, which makes the whole McCormick scheme analog and continuous time. So this is ongoing. So we have actually fabricated the first chip that can solve nonlinear acoustic problems very fast, again in 180 nanometer. So the chip is back. And I don't want to go through too much because it's still unpublished, but at the moment, we are going through very extensive testing and debugging. So I will leave it at that. A brief history of what we've been doing. So the very first chip that we fabricated was for linear finite difference time domain techniques, Maxwell's equations, and that was published in Journal of Solid State Circuits. So that consisted of most of the talk today. Then we also did a discrete time version using switched capacitor techniques. That led to a second JSSC paper, but we didn't really discuss that today. We did 2 other chips using current mode 2-dimensional Maxwell's equation solver that is unpublished at the moment. And the nonlinear solver, the chip is back and is being tested. So we are halfway through the chip generations. But the first 2 chips have been fully published, so we can talk about those things. So in conclusion, analog computing is suitable for some specialized computing tasks. For example, analog computing can be good for scientific computing applications which require extreme speed and very high energy efficiency, which means that essentially at the edge, right? Mobile robotics, other systems. If you want to do very low power budget and very high throughput, and you are willing to give up some programmability, willing to go through some pain into making it work, and also live with some inaccurate results up to a certain margin that you can choose, then analog computing is a preferable choice. It's not a solution for Moore's law, right? I mean, you're not going to run Facebook on analog computers, right? But it's good for certain types of applications. For example, applications that are either very clear mathematical techniques. For example, matrix vector multiplications for AI and machine learning, or solving coupled partial differential equations for physics problems. So these are 2 well-known examples now. So our talk, or our project that I talked about today is not about machine learning. It's about solving physics problems. So we talked about two techniques. The first technique is only for linear systems, and it is based on Laplace theory. The second technique works for both linear and nonlinear systems, and is based on finite difference techniques. So we went into detail of the finite difference technique in analog, and our first CMOS chip, 180 nanometer, 2 millimeter by 2 millimeter chip, consumes 200 milliwatts, was measured to be about 400 times faster than a high-end GPU. The GPU specs, there's no way to measure it, but the power consumption is less than 200 watts. And the analog chip was 200 milliwatts. So that tells you how efficient the analog computing scheme can be. We also tested our analog chip against high-end GPUs, Intel Xeon CPUs running Red Hat 64, and high-end FPGAs, basically Xilinx RF SoCs. And in all cases, the analog computing chip turned out to be way faster, but at various levels of performance. It's always a compromise between performance, power consumption, and accuracy, and repeatability, right? So we are not saying one is better than the other. It really depends on the application and the particular situation. So finally, a little bit of publications that we have done. So we got two papers on the radio frequency analog computational platform, that's linear system, in JSSC, another analog computing paper in JSSC about switch capacitor, and two papers in TCAS1, and a bunch of ISCAS papers. So you're welcome to look at that, and I would be more than happy to answer questions, or either after the talk during the question time, or you are more than welcome to email me, and we can set up a Zoom meeting, or we can communicate over email. I will be happy to talk to anyone about this. So finally, a huge thank you to the Defense Advanced Research Projects Agency, or DARPA, Defense Science Office, that supported this work through an STTR Phase 1 and Phase 2 grant through our friends at Oceus Technologies. So big thank you to everybody. Thank you to Guilherme for inviting me and all the organizers. And also a huge thank you to my PhD student, Hasanta, who has really put in a lot of work for the slides. So thank you so much, everyone. All right. So
thank you very much.
Yeah. Questions?
Thank you very much, Professor Arjuna.
My pleasure.
It was very nice talk, very interesting, really. I'm looking for, waiting for some questions from the audience. Of course, I have several questions of my own, because this is really a topic that interests me. I will start first with one of the first comments that you made in the presentation, that was that the analog computing was maybe not good for accuracy, but good for power, right? Well, I understand that this may be like a trade-off when you compare,
yeah,
because it's based on a noise figure and a signal-to-noise ratio, right? So if you increase the power in the analog, you lose a little bit of this power advantage, but you can improve the dynamic range as well.
Things that analog always has, as long as there are thermal excitations, you are stuck with noise. So, so there are certain things that you can do to reduce the noise. Now, if you just imagine an imaginary analog circuit that has no noise and no distortion, then clearly it's going to beat all digital circuits, because essentially you have infinite precision at that point. But that's not going to happen, right? You always have noise. So, so we are looking at techniques, for example, can we do cryogenic analog computing? So people use cryogenic quantum analog computing, but what about classical analog computing? That just to get rid of most of the noise. So that's something that we want to do. We are trying to do that. But noise is some problem that you can't get rid of in analog. And the thing with digital is that you can reduce the noise to any arbitrarily low level by just adding more and more bits. So 16 bits is more noisy than 32 bits, and 64 bits is even less noisy. Ultimately, digital also has noise. That's a fundamental limitation, but you can make it arbitrarily small. So noise is the problem.
Yeah, yeah, it's not easy to really imagine how much do we depend on the noise from the analog signal processing point of view, right?
Yeah.
But I was thinking on analyzing the signal processing in cascading of noise figures, and in this case you almost have to almost need every cell to be like an LNA, right, with very low noise, and then the power consumption will really increase a lot, right?
Right. That's true. So that's right. So the blocks like the multipliers and so this is why we need this huge gain in the op-amps, because it's not only noise. When you close the loop, you have to have low distortion, because the distortion leads to error in the computation. Now, if you compromise that and you have less feedback, then you can increase the bandwidth. Like a good example is like if you are doing a millimeter wave receiver that has a mixer in front. So you can imagine that mixer as an analog computer that's basically multiplying your input signal with a sine wave. It is an analog computer, but its gain is very low, and you can live with the high noisy output, the distortion, because the wireless communication application is tolerant of that. But if you are trying to compute a partial differential equation, then you can't do that. So that's why it really depends on the application, that noise level. Does it make sense?
Yeah. I understand. Yeah, of course. Okay, so this is basically a case of also of power consumption and dynamic range, right? And it's critical to analog, right? That's a big issue.
Yeah, I mean, dynamic range is another big one you mentioned, because the more dynamic range you have, distortion becomes more and more of a problem. Right?
Yeah, of course, yeah. But on the other hand, you sometimes need a very powerful ADCs to bring it back to the digital signal processing, right? And
well, again, that depends on the bandwidth. For example, like in our case, we wanted to do radio frequency. That's why we had to go through this power-hungry ADCs. Now, if you don't need to do 30 million inputs a second, right? You only need to do a couple of 100,000. Then there are very low power ADCs like sigma delta techniques and things like that, which are very well developed that you can exploit. But because the DARPA project was all about speed, we wanted to get the maximum possible out of the technology. We had to go with flash and things like that. So that's why it's really not power efficient in that sense. Yeah, but ADCs can be a bottleneck.
Yeah, good. Okay, so just one thing that you left open, and of course I would look into the papers and get a better picture of that.
Sure.
But could you compare this discrete time signal processing that you have on the last chip or the one before the last, and with this one that you presented today, right? I mean, in terms of performance, did you check on like same problems to verify what was happening?
Yeah, so the digital one was way more accurate, but the switched capacitor nature of it meant that it cannot tolerate the real-time bandwidths that the analog continuous time version had. So that was way more repeatable. Calibration was much less of an issue because it's all switched capacitor techniques. So it is still low power, but it's almost as if that's suitable for an entire different category of applications. I mean, the fully analog and non-sampled version with high bandwidth is really a class of its own if you want to do this stuff on, let's say, wideband receivers output, which has 50, 100 megahertz of bandwidth. You are not going to do switch capacitor on that. So, but for something like ultrasound level, then switch capacitor might be okay. So, yeah.
Yeah. My question is exactly because I do work with switch capacitor transceivers, right?
Okay.
And we have some works regarding not in my group actually, right?
Okay.
But that come to like 200 megahertz bandwidth from Delft University, right?
Okay.
And it's kind of an old work now. It's like from the 2015 actually.
Okay.
And one thing that we notice is mainly the technology, right? I mean, to work with switched capacitor, you really need a very new technology. So the question is, which one were you using in this?
Oh, we were using 180, so mainly for cost.
180, yeah. So when 180 is terrible for switched capacitor, yeah. But it's interesting point of view, really. Right. I would like to look more deeply into that. Yeah. So
that's I think the switch capacitor version is available in that second JSSC paper. That's in the slides. Thank you so much.
Okay. So let me see here. Well, I don't have many additional questions. Can you talk a little bit about this calibration that you said for this metric of the MSD, right?
Oh my God! Yes, that is the biggest challenge, because imagine you have 64 computational nodes in parallel, and inside there could be 20-30 op-amps with different components, and each one has its own capacitive DAC and a control knob. So we are looking at an optimization problem which has several hundred knobs that you got to turn in order for this thing to be calibrated. So it turned out to be the calibration scheme and implementing a calibration scheme that actually converged and got us a result was almost as difficult as designing the whole chip and the whole other part of the project. But the student who did that, Dr. Nilan Udayanga, spent a lot of time, several months, just on the calibration. Because without calibration, you'd come to the conclusion it's not working. Like if you build the chip, turn it on, nothing works, right? So it's very frustrating. So only when we built in our second version, we built in knobs into every single variable and developed some mathematical techniques to actually converge into a solution. And that was working properly, that the thing started to work suddenly. So if anyone's wanting to do repeat analog computing, keep in mind, be prepared to put in a lot of effort into calibration.
Yeah. Just the last question about this calibration, right? Was it a one-time thing, or
it's one time for every power up?
All right.
So once you power up, you got to do the calibration. So the algorithms take a few minutes to run, and all the bits have to be sent in slowly and programmed. But once it's done, it works fine for days. But if you let it cool down again, then again
you have to start again. Yeah. Okay, so thank you very much. Very interesting talk. Very inspiring ideas. Really inspiring ideas.
Thank you so much for having me. My pleasure.
It's very good to have you here.
Thank you. Are we good?
Yeah.
Thanks, Professor Sandro, for presenting the section. Thank you, Arjuna, for interesting talk.
Thank you, and nice to meet you. Thank you all.
Bye-bye. Please keep in touch.